Hello everyone, this is Miss Lim, your physics teacher. Okay, this is the third part of the video for the chapter on energy. In this video, we'll be covering about what is work done as well as power. Okay, so these are the learning outcomes. We will learn about the formulas for calculation of work done, which is force times distance moved in the direction of the force. And then we will also learn about the formula for power, which is energy transferred over time taken. And also the formula for efficiency, which is the useful energy output over the total energy input. Okay, so before we start, let's do a little bit of activation of prior knowledge. The first question, what is the name of the energy store associated with a stretched rubber band? So a stretched rubber band is something that is being stretched, and whenever things are being stretched or compressed, they have something called the elastic potential store. Okay, next, we have a 1000 kg car is traveling at 20 meters per second along a straight road. Calculate the amount of energy in its kinetic store. So we know that whenever we calculate kinetic store, we use the formula half times mass times velocity square. So for this question, it will be half times 1000 times 20 square. You should be able to get the answer of 200 kilojoules. Next, so what exactly is work done? Over here, I have a lady pushing a stroller and I have a boy pushing a tree. Okay, so both the lady and the boy are exerting force on objects, the tree and the stroller. But is work being done in both situations? Okay, in this case, only the lady does work because she exerts a force and the object, which is the stroller, move in the direction of the force. So there's actually a work done by the lady. But in this case, for the guy, there's no work done by the guy because although he applies force or even a larger force, but the tree doesn't move. The tree does not move in the direction of force, so there is no work done. So in physics, okay, work is done. The formula for work done is force times distance moved by the object in the direction of force. Usually, I don't use S. Okay, I go by this formula, which is work done from S. So work done is equals to force times distance. Okay, and then the SI unit for work done is the same as energy because energy is required in order for work to be done. So they both have the same units of joules. Okay, so or work done can also be think of energy being transferred. Okay, just take note that work done and moments have the same formula. Moments is also force times distance, just that moments is force times perpendicular distance between the force and the pivot, while for work done, it is force times the distance moved in the direction of the force. So the distance used for both formulas are slightly different. Okay, so no work is being done when the direction of the applied force and the direction in which the object moves are perpendicular to each other. So an example is over here. So a boy is carrying a power books, so he needs to exert an upwards force to lift this book at this height. Okay, so he maintained the book at this height and he walked forward. So the movement of the books is forward, while the force exerted by the boy on the book is upwards. So we say that the force is perpendicular to the movement of the book. So there is no work done by the boy on the book. Okay, the next scenario. Okay, so the distance in this case is 0, or the next scenario is no work is being done when there is a force, but the object does not even move. So for example, like the boy pushing on the tree doesn't move, like the girl holding onto the book and then standing stationary over there is also no work done because the book doesn't move up. Okay, so you may pause the video to think about whether there is work done for all this sentence. Okay, I'm going to go through the answers now. The first question, a teacher apply a force to a wall and it becomes exhausted. So in this case, the wall doesn't move. So even though there's a force applied, but the wall doesn't move, there is no work done. Next, okay, a book fall off a table and free fall to the ground. In this case, there will be work done because the book falls because there is a gravitational force acting downwards on the book. Okay, since there is a force acting downwards and the book moves downwards, there will be work done. The work done is caused by the gravitational force acting on the book. Okay, next one, question number 3. A waiter carries a tray full of mail above his head by one arm straight across the room at a constant speed. So what happens is there's a tray of food on top of the waiter's head, and the waiter is moving forward. So in this case, there's no work done because I need to exert a force in order to lift up that tray of food. The force is upwards from my head to the tray of food. But the tray of food didn't move up. The tray of food just moved forward according to where the waiter moved. Okay, so the force and the distance move is perpendicular to each other. They are not of the same direction, so there is no work done. Okay, so we go into examples. Over here, a boy pushes a box across a rough horizontal floor. He exerts 5 newtons to move it by 2 meters. What is the work done? So I know I need to apply work done is force times distance. So it's straight away 5 times 2, 10 joules. Okay, next question. A box of weight 50 newtons is being put 2 meters along a horizontal floor by a force of 10 newtons, and then the box is lifted vertically through a height of 1 meter. What is the total work done on the box? So work done is again force times distance. So initially, I don't use 50 newtons, I use 10 newtons because 10 newtons is the force that causes it to move across the floor 2 meters. So it's 10 times 2. And when I want to lift it up, I need to exert a force that can overcome the weight of 50 newtons. So I'm going to use the force of 50 newtons times 1. So it will be in total 10 times 2 plus 50 times 1. I'll be able to get 70 joules of work is being done on the box in total. Next, we have calculate the work done on the box of 10 kg, assuming a frictionless contact between the box and the plane. Okay, so over here, I didn't give a force. I only give you the mass. Okay, but we know that we can convert the mass into a force, which is the gravitational force, the weight. So the first thing you should know that the weight will be 10 times 10, 100 newtons, and the weight, it will always be vertically downwards from the center of gravity of the object. Okay, so in this case, the weight will be like this. And if I were to use this as my force, which is the only force that is given in this question, what distance must I use? Remember, in order to calculate work done, the force and the distance must be in the same direction. So I am going to use the distance of 3 meters instead of 5 meters or 4 meters. So the total work done will be force times distance, which will be 100 newton, not 10 kg. 100 newton times 3 meters, which will be 300 joules. Okay, let's move on into a slightly more challenging questions. Okay, you have a boy which pulls a 1 kg toy wagon along a smooth horizontal floor over a distance of 5 meters. If the speed of the wagon increases at a constant rate of 2 meters per second square, what is the work done by the boy? Okay, so in this case, there's a lot of words, a lot of variables. Okay, remember, it's very hard to visualize and to solve questions immediately. There's a lot of words. There's a scenario given. So the best thing, the first step is to always draw a sketch of what is happening in the question. And in your sketch, you should always label all the variables that is given in the question. So I am going to draw a sketch. So my sketch will start with like that. I have a 1 kg toy wagon. I represent it by a box, 1 kg. It is going to slide along the floor through a distance of 5 meters. So I put down a distance of 5 meters, and the speed is going to increase at a constant rate of 2 meters per second square. Okay, so I hope that you are able to get it that 2 meters per second square is actually an acceleration. It's not a speed. Okay, the speed doesn't increase by 2 meters per second, it's meters per second square. If I don't understand the question, the next thing is to look at the units. You know, meters per second square is for acceleration, it's never for speed. So what he's trying to tell you is this box is going to move faster and faster and faster with an acceleration of 2 meters per second square. So what is the work done by the boy? So when I want work done, I know I need the force times the distance. The distance was already stated in the question. This box moved through 5 meters. So the distance must be 5. But what is the force exerted on this box? So I need to link back to my formula for force. Okay, my force acting on this box, I have the mass and I have the acceleration. You should be able to get that the force acting on it is F equals to ma. So it's 1 kg times 2 meters per second square. So the force acting on the wagon will be 2 newtons. Okay, because there is no other frictional force, it's a smooth surface. So the only force that acts on the wagon is this 2 newton, which is the resultant force. Okay, then so I exert a force of 2 newtons and the box moves through 5 meters, so it's 2 times 5, I get 10 joules of work being done. Okay, next, okay, we have a 100 kg hammer of a power driver is lifted 20 meters above the pile. It is then dropped so as to drive a pile into the ground. Suppose that 15,000 joules of energy is lost due to friction and the resistive force of the ground is 4,000 newtons. Determine the depth of the pile driver. The depth that the pile driver can be driven into the soil. Again, there is a scenario. I am going to draw diagrams to simplify my thinking. So my diagram will look like this. I have a 1 kg hammer right at the top, 20 meters above the pile. Okay, so I just draw like that. 20 meters, one box with 100 kg. So it is being dropped down, and in the process of being dropped down, it loses 15,000 joules of energy because of friction, air resistance, etc. So this 15,000 will be an arrow going out in the process of it dropping down. Okay, and then next, after it drops down, it will drive the pile into the ground. Okay, and in the process of driving the pile into the ground, there is a resistive force of 4,000. So the 4,000 newton is exerted on the ground, or is exerted resistive force of the ground. So I put this 4,000 here underneath the ground. And because of this resistive force, this power will go into the ground, but it will not go in forever. It will stop after a period of time. So we need to determine what is the distance that the power can go into the soil. Okay, so this is what you draw based on what information is given in the question. Okay, next you need to think a little bit, how is this or where do I start from after I draw the diagram? So you should know that this is my thinking process. You should know that the hammer, initially at 20 meters high, it has GPE. As it drops down, the GPE is being converted to kinetic energy. Okay, just before it touched the ground, all the GPE would have been converted to kinetic energy. Okay, and then as it goes into the ground, okay, the kinetic energy becomes 0. Okay, the pile eventually stopped in the ground. Okay, because of the resistive force 4,000 newtons. So the kinetic energy is actually converted to internal energy, i.e. internal energy, because of there is resistive force, so there will be heat energy being generated. Okay, every time there's friction, there's air resistance, there will be some energy loss as heat. So there will be an increase in the internal energy. So at the moment, once it reaches the bottom of the ground, the moment when you drive the pile into the ground, okay, the kinetic energy is being converted into internal energy. Okay, so this is what you should be able to get. Okay, so in the process of converting from GPE to KE, 1,500 joules of energy is lost. So the first step, okay, you will see that I calculate the initial GPE, which is MGH, which is 100 times 10 times 20 meters. So this is originally my GPE, but I would have lose 15,000. So I would have minus away 15,000 will be my remaining kinetic energy. Not all GPE is converted to kinetic energy. This 15,000 will be lost. So the GPE minus away the 15,000 joules, you will get the amount of kinetic energy. So the amount of kinetic energy calculated is 5,000 joules. So I would have 5,000 joules of kinetic energy here because of this hammer going downwards. Okay. And then, but that is not what I am interested in. I am interested in how much is the debt over here. So if the kinetic energy is 5,000, all these 5,000 must be lost or must be converted or transferred into the internal store of the hammer and the pile, because you can't say that yeah, so it must all be converted into the hammer and the pile. So there will be 5,000 joules of energy. This 5,000 joules will all become internal energy. Okay, then how do I link the distance to the energy? I know that at this portion, I should have 5,000 joules of energy. But how do I link the energy to a Newton? I can't just use 5,000 minus 4,000 or 5,000 divided by 4,000 because they are not the same quantity. This is energy in joules. This is force in Newton. Okay, and there's no such formula as work done over force. Oh, there is lah. Okay, so there is a formula, okay, that links it, okay, to energy, force to energy. The only formula that links it is work done. Work done equals to force times distance. The work done is used to overcome the kinetic energy, so all the kinetic energy is 0 now. Okay, so the amount of energy that I need, okay, to stop it is 5,000 joules. All the kinetic energy must disappear, 5,000 joules. So this 5,000 joules will be equals to the force times distance. The force is given 4,000, and then you find the distance. Remember, there is only one formula that links force to energy, which is work done equals to force times distance. Many a times, when you couldn't solve it using principle of conservation of energy, you need to make use of this formula that work done is force times distance. And the force can come from many different ways. Okay, it can come from resultant force or the individual thrust force or air resistance or tension or friction. Okay. Next, we'll move on into power. Okay, so we are going to take a look at two different scenarios. In the first scenario, boy A and boy B have the same mass, but boy A took a much faster time to climb up the flight of stairs. Okay, so since the two boys have the same mass and they travel the same distance, which is up the flight of stairs, they do the same amount of work. But because boy A reaches the top faster, it takes a shorter time to finish the same amount of work as boy B. We say that boy A has more power than boy B, or boy A is more powerful than boy B. Okay, because boy A can finish the same amount of work in much shorter time. Okay, then we have the second scenario whereby boy A has a much larger mass than boy B. So in this case, since the mass of boy A is more, okay, and even though they reach the top at the same amount of time, because of the larger mass of boy A, more work has to be done for boy A than boy B. Because of his larger mass, he needs to exert more force in order to push himself up the stairs. So work done is force times distance. As the force increases, the work done increases. So the amount of work done by boy A is more than the amount of work done by boy B in the same amount of time. So again, we say that boy A has a higher power than boy B because he can do more work in the same amount of time than boy B. Okay, so we come into the definition of power. What is power? Power is defined as the work done or energy transferred per unit time. Okay, so in formula, it looks like that. Power equals to work done over time or energy over time. Work done and energy are both the same. They are measured in joules. You need energy in order to do work. Okay, so the formula is like this, but usually I don't remember the formula in this way. So I usually remember it by the triangle format, whereby I have power equals to energy over time. Okay, so I go by EPT. Okay, the formula EPT is triangle. Okay, so next, an example of what is the power means. Okay, so in this case, I have an electric kettle. This electric kettle is rated at 1,500 watts. Okay, usually you can find ratings of electric kettle or any electrical appliances on the appliances itself. There will be a sticker or there will be a label that states its power. So in a 1,500 watt electric kettle, it simply means that in every 1 second, I will be able to convert 1,500 joules of electrical energy, okay, into internal energy to heat up this water. So the amount of energy transferred electrically from the power source to the internal stores of the heating element and the water will be 1,500 joules in 1 second. Okay, so that's what does the 1,500 watt means. Okay, next we look at the formula for efficiency. Usually in an ideal situation, okay, we always want that I put in this amount of energy, I must come out that amount of energy, equal amount of energy as how much I put in. That's in an ideal machine case where the total energy output is equals to the total energy input. But in real life, this is most of the time not going to happen because there's always a lot of friction, air resistance, and many other things going on. And so the energy output of a machine is usually much lesser than the energy input. So there is actually a formula for calculating of the efficiency of the machine. It's the useful energy output, how much energy that comes out over the energy that you go in times 100%. That will be the efficiency. So we look at a few work examples. The first work example, an engine does 60,000 joules of work in 10 minutes. Determine its power. So I'm going to use my triangle, EPT. I am interested in power, so it will be energy divided by time. So I get 60,000 joules divided by my 10 minutes. I need to change my 10 minutes to seconds because it must be in SI units, which is seconds. 10 times 60 seconds, I'll get 100 watts. Okay, next question. So I have a kettle that is rated at 1850 watts. Determine the maximum amount of thermal energy that it can generate in 1 minute. So I am interested in the energy. So again, I'm going to use my formula. Energy is power time, EPT. Okay, so I'm interested in energy. So energy is power times time. So the power is 1850, then times the time. 1 hour, again, I need to change it to seconds. So it'll be 1 hour times 60 times 60, 3600 seconds. So I get 6.66 times 10 to the power 6 joules. Okay, next, we move on into work example with efficiency. It says that an electric motor in a washing machine is rated at 1 kilowatt. The efficiency of the motor is approximately 40%. What is the amount of useful energy output produced in half an hour? So I know I'm trying to find energy. So I have my first formula, energy is power times time. So I have 1,000 watts. 1 kilowatt is 1,000 watts times half an hour, means 30 minutes times 60 seconds. Okay, so this is the amount of energy that is being input into the washing machine. 1.8 times 10 to the power 6. But the useful energy output is only 40%. So I need to use 1.8 times 10 to the power 6 and times 40% of it. So the amount of energy that comes out of the washing machine or that is useful in the washing machine, maybe to spin the drum, etc., is only 7.2 times 10 to the power 5 joules. The remaining 60% is lost to the surrounding as internal stores, or lost to the surrounding as sound energy, etc. Okay, so the concept of efficiency is very, very important in power stations. Okay, currently our Senoko power stations, our efficiency is only about 40% to 50%. It means that when you burn the fuels, actually a lot of energy is not being utilized by the power stations to produce electricity. Only 50% comes out. The remaining 50% to 60% is being lost in terms of internal stores of the surrounding, of the machines, of turbine, etc. So scientists, in order to get more energy, scientists is also looking at how can we increase the efficiency of our power station so that with the same amount of fuel burn, I am able to generate more useful output energy. I'm able to generate more electricity to meet the demands for energy. Okay, so in the next part, how can we obtain energy? I'm not going to go in that because you are supposed to go and do research by yourself. So I'm just going to briefly go through that. In this part, we are going to discuss about the use of non-renewable energy sources and renewable energy sources to generate electricity in terms of the efficiency of the energy transfer, the cost, reliability, as well as their environmental impact. Okay, so this is the Singapore energy story. You may go to the YouTube video to search for it. Okay, currently our main energy source comes from the burning of natural gas. And we have 4 switches. You may want to go and research more about the 4 switches. Okay. And in Singapore, we are a small country faced with a lot of limitations in terms of natural resources, land space, materials, etc. So whenever we are dealing with energy, it's always we need to consider 3 different factors, which is called the energy trilemma. We need to consider environmental sustainability. Okay, whether the method of producing energy does it harm the environment? Is it sustainable? Do we have the materials to go on? Okay, and then energy security, meaning my energy supply will not get disrupted. Okay, it will not depend on weather. For example, on certain days there's heavy rain, or on certain days there is no sunlight, etc. Or on certain days where there's a drought, there's no water. Will my energy still continue? Okay, to be able to supply to the whole of Singapore. There's energy security as well as pricing. Okay, there can be ways to produce electricity and ensure energy security, but if it comes with a very high price because of maybe the technology is not there, you need a very high technology to extract the energy. So the cost of electricity will rise, and we want to keep the cost of electricity low. Okay, and so that everyone in Singapore can afford electricity. Okay, so you may watch the video yourself. Okay, so basically we have non-renewable source of energy like fossil fuels. These are the advantages and disadvantages. I'm not going to go through every single one. And then we have also nuclear fuel. Nuclear fuel is something that Singapore is looking into in the near future. Okay, and then we have renewable sources like biofuel, wind energy, tidal energy, hydroelectric or hydropower electricity, geothermal reservoirs or geothermal energies. Okay, solar energies. So basically, these are the few renewable source of energy that Singapore is looking at. Okay, so I will stop here for now.